बोरेड्डी पेटी रेड्डी, दीपक कुमार कल्याण भाई, गौतम कुमार, ज्योति सिंह, ऋषिराज जायसवाल।
प्रेजेंट सर।
चलो हम अटेंडेंस ही ले लेते हैं, जो प्रेजेंट है तो खुद ही बता देंगे, जो बाद में आना तो बता देना, ठीक है ना। पता है कि हम अब मैनुअली अटेंडेंस ले रहे हैं रजिस्टर में, ठीक है। तो अभिजीत सिंह है?
यस सर।
अजय शुक्ला?
यस सर प्रेजेंट।
अलबावली? अलका यादव? अमृतांशु मिश्रा? एक्चुअली कुछ स्टूडेंट्स के मेल जीमेल वाले मेल नहीं थे अपने पास, उसमें इंफॉर्मेशन नहीं गई होंगी, तो इट्स ऑल ऑफ योर रिस्पॉन्सिबिलिटी टू इन्फॉर्म ऑल स्टूडेंट्स। अमृतांशु मिश्रा?
यस सर प्रेजेंट।
भावना अग्रवाल? बोरेड्डी? दीपक कुमार कल्याण भाई? गौतम कुमार?
यस सर।
ज्योति सिंह? ऋषिराज जायसवाल? सत्यम तिवारी? ऋषिराज देयर भाई, यू आर नॉट फॉलोइंग हियर। ऋषिराज?
यस सर।
सत्यम तिवारी? सत्यम तिवारी? शिवा बिंद? शिवा बिंद? शिवांग सिंह? सुचिता जैन?
प्रेजेंट सर।
सौम्य रंजन कुंडू?
यस सर।
सुरभि यादव? सुरभि यादव? तन्वी बंसल? विजय कुमार? 2021 PE 90?
Yes, sir.
विजय कुमार?
यस सर।
विजय राजोतिया? PE 20? विजय राजोतिया? विपुल राजपूत? PE 21?
सर विजय राजोतिया प्रेजेंट।
ओके।
यस सर।
अभी स्टूडेंट्स अभी यहाँ पे नहीं आए हुए हैं। अलबावली, अलका यादव, भावना अग्रवाल, बोरेड्डी, दीपक कुमार, ज्योति सिंह, सत्यम तिवारी, शिवा बिंद, दिवांग सिंह, सुरभि यादव, तन्वी बंसल and Vipul Rajput. Okay. Now I start with some introduction of the syllabus and then subject topic. So can you see the screen there?
Yes sir.
So I will introduce you first about the syllabus of this advanced electrical machines. So here you can see the review and analysis. Okay. Direct current machines, reference frame theory, symmetrical induction machines, synchronous machines, theory of brushless DC machines, winding functions and machine design, machine equation for improving analysis and modeling of machines coupled to power electronic circuits, analysis of unbalanced operation, generalized approach to machine parameter identification, linearized machine equations, reduced order machine equations, and switched reluctance motors. Okay, so some of the reference books are given here, and later as the classes go on, I will be introducing about the books from which book which section has to be covered. Okay, so presently I am starting with a basic introduction of basic principles and introduction of the electrical machines. So I have a PPT for you. So the basic some basic principles of electrical machines are Faraday's law and Biot-Savart law, uh, Stokes theorem and Gauss's theorem. So here you can see there is a closed loop containing the current. Suppose there is a current carrying conductor and it is making a closed loop, and there is a flux density either going inside the conductor plane. This you have a surface S made by the closed loop of the conductor, and either it can be also induced by the conductor itself. So here the relation is between the induced EMF in whole of the length of the conductor, and this is the line integral along the total length of the conductor, and here you can see the flux density B and the surface area ds. So BDS represents the total flux through this surface made by the closed loop C. Okay, so the Faraday's law tells that the induced voltage is equal to minus of d phi upon dt. How it comes? It comes through the Stokes theorem. Stokes theorem is that the line integral along a length is related to the surface integral. In any surface, suppose that flux density B is there and the surface S, then this will be the relation which is told by Stokes theorem. So you can see here the E is the curl of E will represented by the B. Okay, so Stokes theorem, I will tell you what is the Stokes theorem here. Here you can see the Stokes theorem that the integral in a closed loop along a length L is given by the curl of A into ds. Okay, so here by comparing this equation, you can see that the curl of B is equal to curl of E is equal to the flux density B. Okay, in this PPT, you can see that this flux density B is the curl of induced EMF E. Okay, so here induced EMF E into dl in the closed loop, and flux is represented by the sorry, here E is the electric field in which is represented in the perpendicular to the conductor's conductor cut section. So here you can see that the induced EMF P is equal to the electric field, the line integral of electric field along the whole conductor length, and the flux is represented by the flux density into the surface. Clear? Have you got this point, students?
Yes,
Is
sir.
it clear?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
तो ये सिंपली जो है द कर्ल ऑफ electric field E is equal to the magnetic flux density B. Okay, if we see the Stokes theorem here, if you have this E here in place of A, then curl of E will represent the magnetic flux density B. Okay, so induced EMF is represented by the line integral of electric field along the whole conductor length, and the flux will be represented by the surface integral along the whole surface made by the closed loop. Now we come to the next slide. This says that EMF around a closed loop. So this is simple explanation of the same thing, and here, because BDS is the flux, so here we have replaced this flux, BDS as a flux. So here d by dt, and this this is replaced by the, so you can see that induced EMF is equal to minus d phi upon dt. Here you can see that minus is a term which comes from the Lenz law. So what the Lenz law says, according to the Lenz law, the suppose that we have imposed a magnetic field in any conductor, then that conductor will have such a current that it will oppose the magnetic flux density, and it will induce the flux in the opposite direction. So this is Lenz law. So the induced EMF will such that the current setup will set up and set up a flux in opposite direction to the given flux. Okay, so this minus is for that. Here this is the third part, and here you can see that how the, here you can see that the conductor cross sections are showing here, and the current direction is shown. Okay, so in along the any conductor, suppose here you can see a conductor, and this cross section is shown, current is coming upwards. Okay, so the induced applied magnetic flux will induce a induced voltage in the conductor ends. Okay, so this is the Lenz law, which is defined. This is red color arrow shows. This is for Lenz law. Okay, the EMF induced in the contours is of a polarity that tends to generate an induced current whose magnetic flux tends to oppose any changing original magnetic flux. Now we have Faraday's law for multiple number of turns. Here you can see in previous slide we have given the induced EMF for one number of conductor, one number of turn, and so if there are a multiple number of turns and magnetic flux density B, then there will be a induced EMF will be n times the induced voltage in one turn. Suppose there are n turns, so the induced voltage be multiplied by n, because there are n number of turns, and this EMF all will add together, because all are in the same direction of polarity. So here you can see that a coil is there, and this is a coil, and a flux is coming inside the coil, and suppose it is changing, flux density is changing, and depending on the change of flux density, there will be induced voltage also. Okay, so can without any change of the flux, there is no any possibility of induced voltage, because V induced equal to n times the d phi upon dt, and if we use also the Lenz law, then V induced equal to minus n and d phi upon dt. Clear, students? Is it clear?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Yes. Yes.
Now come to the operation first, like the generator. Here you can see that there are n number of coils, n number of conductors in a coil. Coil is a set of conductors, okay, and there in each coil there occurs two sets of conductor sides, okay. So here, how many number of conductors are there? Three number of conductors in a coil, okay. So coil is one, and three number of conductors are there in one side, and total number of conductors are 3 into 2. So suppose this coil is put in a magnetic field, such that field B external is applied in this coil, okay. So after applying this V external, there will be induced voltage in this coil V induced, that is plus and minus, okay. So suppose if we take this coil represents the plane of the paper, and the magnetic flux B external is upwards in the plane of the paper, okay. Clear है यहाँ पे? If you see here the dots, suppose that the dots represent the direction of magnetic flux upwards, okay. तो अगर ये क्वाइल है और डॉट्स अप साइड हैं, तो इंड्यूस्ड ईएमएफ क्या होगा? दैट विल बी गिवन बाय द राइट हैंड पाम रूल, ओके। राइट हैंड पाम रूल क्या है कि अगर आप एक पूरी फिंगर्स को आप स्ट्रेट कर लेते हैं, ओके, आई विल टेल यू बाय सम व्हाइट बोर्ड. Suppose we have suppose this is our hand, and these are the fingers, and we have done our fingers straight, and this is palm, and this is left hand. In the left hand, suppose these are the lines of hand, you can see here, okay. So the field is in this direction, and if the force or movement is in this direction, the current will be in this direction, okay. And in case of मोटर के केस में क्या होगा कि ये हमारा लेफ्ट हैंड है और राइट हैंड है, और ऐसे these are the fingers here, and this is the thumb, and this is the inner part of this hand. Okay, some lines are there, you can see in the inner parts of hand, and you have the field direction in this. Okay, and you have the current in this direction. You have set up the current in this direction, then there will be a motor action, force will be applied to this conductor. So this is the right hand rule and this is the left hand rule. Okay, so from both the systems you have represented both the hands, you have represented the direction of force in perpendicular to the plane of the palm. Okay, and the direction of thumb represents always the current, and the direction of magnetic flux represented by the multiple number of fingers, that multiple number of lines will represent the flux. Okay, then here this is the generating action and this is the motoring action. Then here you can see that the flux is upwards. In case of flux is upwards, what will be the direction of current in any conductor? Here this is the conductor and flux is upwards. In that case, what will happen? Any student can answer. Suppose, can you see my arrow here? Can you see my arrow? This?
Yes, sir.
Yes, sir.
So where my arrow is there and magnetic flux is applied upwards and the conductor is moving, then what will be the direction of current? Here in this direction. Okay, in this direction will be current. Clear? The coil is moving upwards here in this direction and magnetic flux density is upwards. Then what will be the direction of current? Like this. Okay, so in the same manner here you can see that the external magnetic flux is applied, and when a current will be when we apply a resistance R or any load, then a current will be set up. Suppose that after applying the external magnetic flux, an induced voltage is generated in the winding terminals, and then if we apply a resistance, a current will be set up. So after a setup of this current, a secondary flux will also be introduced, which will try to oppose the externally applied magnetic flux. Okay, is it clear? So here you can see that B external is in upwards direction and the induced flux density is in downward direction. Clear? So total magnetic flux density B is the resultant of both the flux densities. So B is equal to B external minus B from the setup by the induced current. Okay, so B external minus B I. Now we come to the flux. The same formula will be for the flux also. Phi equal to total flux passing from the coil. Okay, this is the solenoidal coil, and the total flux given is the B dot ds, that is surface integral of B external dot ds minus Bi dot ds. Okay, so this B external dot ds is the total applied flux from the external source, and the I from I is the induced flux after induced current in the coil. So induced flux will be opposite to the externally applied flux. So here you can see V induced is equal to N d phi upon dt. Now here you replace the phi external minus phi from I, then the induced voltage will be equal to N d phi external upon dt minus N d phi from I upon dt. Clear? Now here you can see that this is total flux linkage. N phi is the total flux linkage. N phi is called the total flux linkage lambda. So here for N phi you have replaced the lambda. Okay, clear? Total flux linkage from the coil due to current I is N phi. This is the lambda, that is equal to N phi. Any confusion on that?
No, sir.
No, sir.
So here after replacing, because d lambda upon dt, the flux linkage lambda is also equal to the Li. Okay, because Li equal to N phi, this is the total flux linkage. So lambda is replaced by here Li, then d lambda upon dt is replaced by L di upon dt. So total induced voltage in the coil will be equal to N d phi external upon dt minus L di upon dt. Clear?
Yes, sir.
So now you see that V induced has been spent on the total induced voltage has dropped on the resistance. So V induced equal to Ri. Clear? So here if you replace this V induced equal to Ri, then N d phi external upon dt minus L di upon dt equal to Ri. Clear? N d phi external upon dt minus L di upon dt equal to Ri. Now when you set aside this di upon dt, okay, then what will be the final equation? The dynamic equation in the coil for current dynamics is given by di upon dt equal to minus R upon Li minus N upon L d phi external upon dt. Clear? Next is the case for the motor. Suppose that you have a magnetic flux in upwards direction of the plane of the paper, okay, and a coil is in the plane of paper. Okay, तो B का डायरेक्शन क्या है? परपेंडिकुलर टू द प्लेन ऑफ पेपर एंड coil is in the plane of paper. ठीक है? और here suppose movement or change of the flux is in such a direction that there is a current in the you apply a voltage source Vs here, and after applying a voltage source Vs and a resistance R, there will be a certain, this R may be the external resistance or may be assumed to the resistance of the coil, or it can combine both the external as well as the resistance of the coil itself. Okay, so a generalized representation is given for overall resistance of the circuit. Okay, so after the Vs is applied in case of motor, Vs voltage source is applied, then there will be a drop in the resistance, and because this is the closed circuit, so current I will be set up. So this current I goes in this direction, suppose. Okay, so here suppose this end you are taking, then there will be a movement in the coil. Okay, so there will be rotation. So what will happen here? In the this coil will start to move. So this is given by the right hand palm rule. Here the direction of fingers is upwards, is the magnetic field, and here the current direction is given by the thumb, which is given by here upwards direction in the plane of paper, you can see here. So the movement will be, for this conductor, the movement will be uh, right side. Okay, so the coil will start to move. Here you can see that another view of the same coil is given. R is applied, and induced current voltage supply Vs and a resistance R. A current is set up due to this closed loop circuit. Okay, after introducing a field, magnetic field by this current, there will be opposite to the there will also be the because there is a flux is linking, there will also be an induced EMF. Okay, so if there is induced EMF, then the total current will reduce. If induced voltage is 0, then the current will higher. In case there is certain induced voltage which is greater than 0, the current will reduce. So here current is given by Vs minus V induced upon R. Here V induced upon R is the induced voltage in the coil due to the flux linking itself, because coil has the quality, Lenz law says that every flux will be opposed. Okay, तो यहाँ पे क्या होगा, induced voltage will be equal to the ND phi equal to LdA upon dt. So dynamic equation is given by here. Dynamic equation is given by dA upon dt minus R upon Li plus Vs. तो ये सिंपल इक्वेशन है. V जो जितना भी होगा V इक्वल टू Ri plus LdA upon dt, or it can also be given as Vs equal to Ri plus Nd phi upon dt. Okay, because LdA upon dt equal to Nd phi upon dt. Simply this is for the case of motor. Now suppose there is a magnetic field B, and there are two parallel conductors which are charged. Okay, so one is with positive charge and one is with negative charge. A potential is there between these two conductors. So V induced is will be the either it can be applied voltage in case of motor, and it can also be the induced voltage due to the movement of conductor in this magnetic field. So suppose we are taking the case for a generator. So in that case, suppose the direction of flux is downwards, perpendicular to the plane of paper. ये downwards है, you can see the crosses here. The direction of fluxes is downwards. Clear, students?
Yes, sir.
Yes,
Yes,
sir.
sir.
So direction of flux is downwards. and a conductor movement is done by velocity v. Suppose we are moving manually, or it can be from some other technique. There is a movement of this conductor, and this conductor, two ends of this conductor is placed in a common parallel conductor lines. Okay, so if we move this conductor in this magnetic field, then the overall flux with which this conductor is cutting is B into area of this flux area. Okay, so total flux area is A and the magnetic flux density is B. So total flux cut through the movement of x मूवमेंट है और L कंडक्टर की लाइन है, तो टोटल जो एरिया होगा दैट विल बी DL A equal to LX and B equal to the magnetic flux density. Conductor is BLX. Clear? In that case, for a single conductor, because this conductor is single, there are not multiple turns. So for single conductor, the induced voltage will be equal to d phi upon dt. So BL into dx upon dt. Now here you can see that the velocity v is the derivative of displacement x. Okay, so induced voltage equal to BLV. Is it clear?
Yes, sir.
Yes, sir.
Yes,
Now
sir.
come to the next point here. Suppose this by Savart's law, ठीक है ना? This is represented for the motor. Suppose there is a magnetic flux density B downwards perpendicular to the plane of paper. Plane of paper is the plane of PPT you are looking. Okay, so downwards है flux का direction and there is a current I. Current I is downwards. We can see here directly the current is downwards. So this is the motor case, and in case of the motor there will be a force generated. Here in the previous section you have seen that we have applied external force and we have moved the conductor with velocity v. Then there will be there was a induced voltage. This is the generator case. However, in this Bio-Savart's law and this motor case, you see that the current is downwards and magnetic flux is downwards. Then there will be a force generated. This is a motoring action. So which hand gives this rule? किधर का फोर्स होगा? कोई बता सकता है कि किस हाथ से, किस हैंड से दिया जाएगा इसका जो जनरेटेड फोर्स है उसका डायरेक्शन? Students, please respond. You can see here again. I will show you.
Right
This is
hand,
for motor.
the right hand rule, because
Yes.
this is
Yes.
motoring action.
Yes. This is motoring action. So you will give the right hand. Now you direct your fingers downwards to the perpendicular to the plane of paper. Then and the thumb, you direct your thumb downwards. Then what will be the direction of force? Direction of force will be exactly the same which is shown here. Okay, you can do it manually wherever you are there. You can do it manually. Check it how the directions of force are decided. तो ये force that incremental force will be depending on the, this is the Bio-Savart's law. Okay, that IDL in a closed length there is a conductor and total integral of incremental force equal to total integral of along the length conductor current I along the length in multiplied by magnetic flux density B. तो इसका बायो-सावर्ट्स लॉ से डायरेक्ट रिलेशन है. So the force in the conductor is given by the VLI. Okay. So in case of motor, using the current I in the conductor and flux density B, we can estimate the force. Okay. In case of the here generator, you can by movement of conductor and by the magnetic flux density B, we can check the induced voltage. Okay. So both the cases have been shown here, and now we come to the motor case at no load. Okay. So in case of no load, what will happen? No load means we are not applying any force externally. Simply the conductor is under the magnetic flux density B, and it can be the commutator bars or it can be the slip ring for two conductors. अगर हम इसको अपर कंडक्टर को स्लिप रिंग बना दें, नीचे वाले भी कंडक्टर को स्लिप रिंग बना दें और एक कार्बन ब्रूस के थ्रू हम इस चीज को कनेक्ट कर दें, तो this conductor will have always the constant polarity of terminals. ठीक है. तो यहाँ पे हम सपोज कि कंडक्टर मूवेबल है, तो इसलिए स्प्रिंग कारण दूसरे चीजें जरूरत पड़ सकती है. नाउ सपोज V बैटरी is applied, okay, VB, and at t equal to 0 the switch is turned on. Resistance R is suppose the total circuit resistance. Then depending on this resistance, a current I will be introduced in this closed loop circuit. Okay. After introducing the current I in this closed loop circuit, there will be a force, induced force in the conductor VLI t equal to 0. Okay. Is as soon as we turn on the switch, there will be a force on the conductor. Clear? And this force, because this force will be applied to the conductor, and conductor has certain mass, and it will reach to the certain acceleration and velocity. So whole of the induced force is spent on movement of the mass. So m dv upon dt equal to mass into acceleration equal to F induced. Clear? So there will be acceleration if F induced is greater than 0. The dv upon dt will be greater than 0. So in that case, the motor will, the conductor will accelerate. Clear? After acceleration, now because the conductor is accelerating in a magnetic flux density B, so there is a certain velocity of the conductor, so there will also be an induced voltage by generating action. ठीक है. तो इंड्यूस्ड वोल्टेज भी तो होगा, क्योंकि जब भी मूव होगा कंडक्टर वो एक वोल्टेज भी इंड्यूस करेगा. ठीक है. यहाँ पे तो ये था कि हमने सप्लाई करंट दिया तो यहाँ पे फोर्स बनेगा, दिस इज द मोटर केस. बट जैसे ही ये कंडक्टर का मूवमेंट होगा उसी फील्ड में, देयर विल बी अ सर्टेन induced voltage also. So now suppose induced voltage is something greater than 0, then the current will reduce. अगर 0 है induced voltage तो शुरू में t equal to 0 पे there is no induced voltage, so full current will be there VB upon R. However, in case the conductor has itself induced some voltage V induced, then the current will reduce VB minus V induced upon R. Okay. So in that case, जब करंट ही रिड्यूस हो गई, इन दैट केस फोर्स विल आल्सो रिड्यूस बिकॉज फोर्स इज रिलेटेड टू BLI, जो भी कंडक्टर में करंट है, मैग्नेटिक फ्लक्स डेंसिटी भी है, तो डिपेंडिंग ऑन दैट देयर विल बी ए इंड्यूस्ड फोर्स। तो जब हमारा करंट घट गया, इंड्यूस वोल्टेज इंड्यूस होने के कारण करंट घट गया, तो इंड्यूस्ड फोर्स भी घटेगा। तो पहले एक्सेलरेट हुआ फिर घट गया, तो एक सर्टेन कंडीशन आती है कि व्हेन देयर इज अ इंड्यूस्ड फोर्स इज 0, ठीक है। तो इन दैट केस क्या होगा, मशीन स्टेडी स्टेट में जाएगी और कांस्टेंट वेलोसिटी से, जब कोई फोर्स अप्लाइड नहीं होगा तो जो भी पहले मूवमेंट है वो एक्सेलरेशन, जो भी वेलोसिटी है उसकी वो मेंटेन रहेगी। अगर कोई फोर्स इंड्यूस नहीं हो रहा है, सपोज हम किसी चीज को एक्सेलरेट करके और फिर उसमें कोई फ्रिक्शन फोर्स या कुछ भी नहीं लग रहा है, ठीक है, एक्सेलरेट हो गया, कोई भी फ्रिक्शन फोर्स या मास वगैरह का फोर्स कोई भी नहीं लग रहा है, इन दैट केस जो वेलोसिटी है उसकी मेंटेन रहेगी। कौन सा न्यूटन का कौन सा नियम है ये, व्हाट इज दिस प्रिंसिपल ऑफ न्यूटन?
फर्स्ट लॉ सर। फर्स्ट लॉ सर।
हाँ, तो ऐसे ही ओके। तो जब यहाँ पे अगर हम कंडक्टर है, सपोज दैट इज इज फ्री टू मूव इन दिस पैरेलल कंडक्टर्स, तो कोई फ्रिक्शन फोर्स नहीं लग रहा है, मास का अगर इसका मास कम है, बहुत कम है, नेग्लिजिबल है, उस केस में क्या होगा, स्टेडी स्टेट, एक कंडक्टर का मास कितना होगा, तो ये स्टेडी स्टेट में पहुंचेगा, तो क्या होगा, इंड्यूस्ड वोल्टेज इक्वल टू BLV and the velocity of the conductor can be given by the V induced on VL. So here we can estimate the velocity of the conductor in case we have turned on the switch. Okay, तो जैसे ही हम मोटरिंग एक्शन में चलाते हैं तो कंडक्टर की वेलोसिटी क्या होगी, सपोज इंड्यूस्ड वोल्टेज चेंज होता रहता है टाइमली, तो देयर विल बी सर्टेन इनिशियल, सपोज इनिशियल वेलोसिटी हाई होगी, फिर इंड्यूस्ड वोल्टेज फिर डाउन हो गया, मान लो स्पीड डाउन हुई, तो उस केस में फिर ये स्पीड डाउन हो जाएगी। तो देयर आर म्यूचुअल रिलेशन ऑफ ऑल दीज पैरामीटर्स, ठीक है। So this is a successive a type of story that you have first applied the battery and a resistance current is set up here. When the current is set up, there will be F induced. F induced will depend on the current I. Okay, and whenever there is a force induced, there will be the movement and there will be acceleration. Depending on this movement acceleration, certain velocity will be there. Depending on that velocity, there will be a certain induced voltage. When the induced voltage is there, the current will reduce because the current depends on Vp minus Vi upon R. Okay, so in that case current will reduce, current reduce होगा तो F induced भी reduce हो जाएगा, F induced reduce होगा तो velocity भी reduce हो जाएगी। In that case जब F induced अगर 0 हो जाए इन सर्टेन केस, तो जो भी कंडक्टर जिस वेलोसिटी पे भी चल रहा है तो वो स्टेडी स्टेट पे आ जाएगा। ओके, तो यहाँ पे यू कैन सी द केस फॉर मोटर एट नो लोड। क्लियर? Here another case is shown that with load, motor case with load. In that condition what will happen, यहाँ पे बैलेंस होगा जब भी टोटल नेट फोर्स will be equal to the F induced minus F load. Suppose induced voltage is due to the current as at t equal to 0 as soon as the switch is turned on. VB is the supply voltage which is turned on t equal to 0, and due to the total resistance of circuit there will be certain current I. Certain current I at t equal to 0, there will be F induced VL I t equal to 0. So in that case the total net force applied in the conductor is equal to the force which has been induced and the load applied. Okay, so F induced minus F load. क्लियर है आप लोगों को?
Yes, sir. Yes, sir.
Yes, sir.
So
Yes, sir.
अगर नेट फोर्स ज्यादा है तो मोटर ये जो कंडक्टर है एक्सेलरेट होगा, और नेट फोर्स कम है तो नेट फोर्स कम होने की कंडीशन में एफ लोड ज्यादा है तो कंडक्टर डिसलेट होगा। ओके, तो अब यहाँ पे भी वही कंडीशन है कि जब जो भी नेट फोर्स है वो ड्यू टू द नेट फोर्स देयर विल बी सर्टेन वेलोसिटी भी, तो कंडक्टर जो है वो नेट फोर्स के कारण मूव करेगा। ठीक है, वो ऐसा नहीं कि इंड्यूस्ड फोर्स के कारण बस ही मूव करेगा, जो नेट फोर्स अप्लाई होगा उसी के कारण मूव करेगा। एक्सेलरेशन ओवरऑल एक्सेलरेशन विल डिपेंड ऑन द नेट फोर्स। तो नेट फोर्स इज स्पेंट ऑन मास इनटू एक्सेलरेशन। तो यहाँ पे अगर इंड्यूस्ड वोल्टेज ज़्यादा है तो एक्सेलरेशन होगा, इंड्यूस्ड वोल्टेज लोड से कम है तो डिसेलरेशन होगा। ठीक है, निगेटिव हो जाएगा टर्म टी वी बाई डी टी, पॉजिटिव होगा नेगेटिव होगा। नेट छोटा है, अगर एफ नेट लेस देन 0 तो निगेटिव हो जाएगा, डिसेलरेशन होगा। तो इस इन ऑल द केसेस देयर विल बी द वेलोसिटी ऑफ सर्टेन वेलोसिटी ऑफ दिस कंडक्टर। तो जो भी उसकी वेलोसिटी है एट दैट टाइम, एट एनी टाइम वेरिंग वेलोसिटी है, टाइम वेरिंग है, तो डिपेंडिंग ऑन दैट वेलोसिटी देयर विल बी ए इंड्यूस्ड वोल्टेज। ओके, वी इंड्यूस्ड। तो जब भी वी इंड्यूज होगा तो फिर क्या होगा, इन दैट केस जो शुरू में हमने टी इक्वल टू 0 पे हम वी इंड्यूज को 0 मान के चल रहे थे, अब वो ग्रेटर देन 0 है। ठीक है, तो डिपेंडिंग ऑन दिस करंट विल आल्सो रिड्यूस, एफ इंड्यूज विल आल्सो रिड्यूस। ओके, जब एफ इंड्यूस अगर रिड्यूस होगा तो उस केस में क्या होगा, धीरे धीरे एक ऐसी कंडीशन आएगी कि एफ लोड इक्वल टू एफ इंड्यूस। शुरू में क्या था कि एफ इंड्यूस शुरू में करंट ज़्यादा थी, शॉर्ट सर्किट थी, डायरेक्ट था, मतलब इंड्यूस वोल्टेज कुछ नहीं था। एफ इंड्यूस ज़्यादा होने के कारण यहाँ पे एफ नेट फोर्स ज़्यादा था, एक्सेलरेशन हुआ। अब ये एफ इंड्यूस 0 हो गया, डाउन वर्ड्स जा रहा है एक सर्टेन केस पे, एफ इंड्यूस इक्वल टू एफ लोड। तो इस केस में क्या होगा, नेट फोर्स ऑन द कंडक्टर इज 0, और वो जो भी वेलोसिटी इस टाइम पे रहेगी उस टाइम पे, तो वहीं से वो वेलोसिटी मेंटेन रही जाएगी। तो इन दैट केस क्या वेलोसिटी कहलाएगी, v इक्वल टू वी इंड्यूस्ड अपॉन वी एल। और जो करंट है उस टाइम पे जो भी करंट है वो दोनों चूंकि नेट अप्लाइड 0 है तो एफ इंड्यूस्ड इक्वल टू एफ नेट, एफ लोड। ठीक है, जब नेट 0 हो गया, दोनों बराबर हो गए, तो उस केस में जो भी करंट फ्लो हो रही है उसका रिलेशन ये है। तो करंट निकाल सकते हैं कि एफ इंड्यूस्ड बाई बी एल एंड यहाँ पे वी इक्वल टू वी इंड्यूस्ड अपॉन बी एल, और वी इंड्यूस्ड इक्वल टू वी बी माइनस आई आर। शुरू में जो भी हम बैटरी वोल्टेज देते हैं, ड्रॉप होने के बाद इंड्यूस्ड वोल्टेज, ये रिलेशन बन जाएगा। एक रिलेशन ये है, ओके, दैट इज वी इंड्यूस्ड इक्वल टू बी एल वी। ठीक है, क्लियर है? ये बी एल वी इक्वल टू वी इंड्यूस एक रिलेशन है, और एक एक्सटर्नल सर्किट का जो रिलेशन है वी इंड्यूस इक्वल टू वी बी माइनस आई आर। ठीक है, तो ये अंदर का रिलेशन है, कैसे निकल रहा है वोल्टेज सर्किट से आफ्टर द एक्शन ऑफ द फ्लक्स एंड मूवमेंट, और यहाँ पे ये जो है बाहर का है, जो नेटवर्क इक्वेशन होता है कि वी इंड्यूस इक्वल टू वी बी माइनस आई आर। ठीक है, तो यहाँ से वी वेलोसिटी वी इंड्यूस्ड ऑन वी एल। ओके, सो आई एंड हियर today's lecture. Any queries you can ask students? कोई क्वेरी है? और जो स्टूडेंट अभी आए हो बीच में?
No, sir.
No, sir.
Uh,
No query.
Excuse
Any
me, sir.
student? Yes.
सर सर आप ये PDF शेयर करेंगे? I mean,
ठीक है, शेयर करेंगे, वो सब मिल जाएगा। लेट्स द लेक्चर गो ऑन।
थैंक यू सर।
तो लेक्चर कंप्लीट होने के बाद हम पीडीएफ शेयर कर देंगे, तो जो लेक्चर कंप्लीट होते जाएंगे। आप लोग नोट नहीं करते हैं क्या?
सर कुछ पॉइंट्स नोट किए हैं सर, पूरा नहीं हो पाया है।
Okay, after the completing this PPT, I will be sharing in 5 section. Okay, 5 सेक्शन में शेयर कर दूंगा, तो आप लोग इसको रिसीव कर लीजिएगा।
सर
तो मैं एक हूँ अटेंडेंस, कोई है तो आप बोल दीजिए। अभिजीत सिंह, अभिजीत सिंह,
Yes, sir.
अजय शुक्ला,
Yes, sir.
अलबावली, अलका यादव, अमृतांशु मिश्रा,
Present, sir.
भावना अग्रवाल, बोरेड्डी, दीपक कुमार कल्याण भाई, गौतम कुमार,
Yes, sir.
ऋषिराज जायसवाल,
Yes, sir.
सत्यम तिवारी, सत्यम तिवारी, शिवा बिंद, शिवांग सिंह, सुचित्रा जैन, सुचिता
प्रेजेंट
जैन,
सर। प्रेजेंट सर।
ओके, सौम्य रंजन कुंडू,
Yes, sir.
सुरभि यादव, तन्वी बंसल, विजय कुमार,
Yes, sir.
PE 19 है,
Yes,
विजय
sir.
राजोतिया,
Present, sir.
ओके, PE 20 विजय राजोतिया प्रेजेंट। विपुल राजपूत, विपुल राजपूत आ गए हैं, विपुल राजपूत, ओके, विपुल राजपूत नहीं है। ठीक है, टोटली 1 2 3 4 5 6 7 8 9 9 students are present. Okay, so all of you can leave now.
Thank you, sir.
Thank you, sir.
थैंक
Thank
यू
you,
सर।
sir.
Thank you, sir.
Okay,
Thank you, sir.
Sir, hello.
बोलो।